Hi, I'm Sean Gannon, and this is Minute Math, and today we're learning about related rates.
Minute Math, when you need help you use Minute Math.
We're given this problem right here. Water leaking onto a floor forms a circular pool. The radius of the pool increases at a rate of 4 centimeters per minute. How fast is the area of the pool increasing when the radius is 5 centimeters? Okay, so let's first draw a picture from what we're given here. We're going to start with a circle, right? So I have a circle here. Don't judge my circle. And we know the circle has a radius, right? Every circle does. And that radius is given to us as it's changing at a rate, so that the rate of the radius over time, dr dt, all right, the rate of the radius is 4 centimeters per minute. Okay, so we have 4 centimeters per minute is that rate of the radius going out. Now, we want to find out what happens when the radius is 5 centimeters. They tell us at the end there. So we want to find what happens when it happens that the radius is 5 centimeters. I can fit that in there. Okay. Now, one thing we want to know is, well, the area of a circle. That's important to get here. So area equals, area of a circle is pi r squared. Okay. All right. So now when we take this related rate, we want to actually derive this formula for the area of a circle with respect to time. Okay, and we're going to get some of the information that we need from there. Okay, and so when we do that, we take the derivative with respect to time, d over dt, of our area, and that's equal to the derivative with respect to time of our other side of the equation, pi r squared right here. Okay. Now, the left-hand side's pretty easy to find. The derivative of the area is, well, with respect to time, is just going to be that dA dt. Okay, pretty easy to find there. Now notice dA dt. They said how fast is the area of the pool increasing at this specific moment. dA dt is what we're looking to find. Okay, so we're on the right track here. The right-hand side, when we derive this with respect to time here, notice that pi is just a constant, so we can take that constant, put it out front. And now we're really deriving r squared with respect to time. Now, the radius here is a kind of a function of time, okay? So when we actually derive this, we have to do a little special thing going on. It's like the chain rule in a way. So we have dA dt is equal to pi, and now using the chain rule, derivative of this we take of r squared, the 2 comes out front, times the inside, that r value, subtract the exponent by 1, so we just have a 1 up there, times the derivative of r with respect to time, which is that dr dt. And now we actually have a pretty good formula. We can plug in what we know. The radius at the moment we're talking about is 5 centimeters. So we have dA dt is equal to pi times 2 times 5, and the units is centimeters, times dr dt, all right, which we know is 4 centimeters per minute. They gave that to us. So we have 4, and its unit is centimeters per minute, right there. So we multiply all this out, and we have 2 times 5 times 4, and that's going to give us our 40, and then the pi, right? So we have dA dt here is equal to 40 pi, and that's our units, centimeters times centimeters per minute is centimeters squared per minute, and that actually works as we're talking about how the rate of an area changes. So that dA dt, what does that equal? Well, that's that 40 pi centimeters squared per minute, not meter, per minute, right there. All right, so 40 pi centimeters squared per minute is our final answer. We're given this problem right here. Oil spilling from a ruptured tanker spreads in a circle on the surface of the ocean. Not good. The area of the spill increases at a rate of 9 pi meters squared per minute. How fast is the radius of the spill increasing when the radius is 10 meters? Okay, let's first get a picture of this. We draw a little circle, and it's a big circle actually because it's in the ocean here, right? But the circle has a radius right there. Okay, now what do they tell us? They give us here that the area of the spill increases, okay, at a rate of 9 pi meters squared per minute. And so if the area, right, the area of a circle is that pi r squared, the rate at which the area increases is dA dt. And they tell us that it's 9 pi meters squared per minute. So we have a 9 pi, and that's a meters squared per minute. Okay. Now, at the moment we said we were finding the radius of the spill increasing when the radius is 10 meters. So the moment we're looking for is a radius of 10 meters. And we want to find the rate of the radius, which is our dr dt. And that's what we have to find. That's what we're looking for right here. Okay? So to do this, we need to derive our function for the area of a circle with respect to time. Okay? So we have, again, that area of a circle is pi r squared. And we want to derive both parts with respect to time. Right there. Okay? So the left-hand side, derivative of the area with respect to time, is just that dA dt. Now, with respect to the radius here, with respect to time of the radius, the pi can just come up front, it's a constant. And the derivative here, we're using the chain rule again. 2 comes down, power, r stays the same, subtract the exponent by 1, so it's 1 there, multiplied by the derivative of the r value, the radius, with respect to time, dr dt. And at this point, we have, well, a lot of information. We can plug in some stuff and actually solve here. dA dt is 9 pi. And our units, they said, was meters squared per minute. And I don't always actually write this out. I kind of ignore the units and put them at the end. That's my preference. And then we have pi times 2 times our radius, right? Our radius is 10 meters, right? So 10, and then units is meters, times dr dt, which we don't know. Okay? Well, now we just have one variable, and it's just algebra to solve. We divide both sides by pi times 2 times 10 meters. Okay, to both sides, pi times 2 times 10 meters. And what happens there? Okay, well, the pi's cancel. And what we have here, and this whole side cancels, okay? And what we got is 9 over 2 times 10 is 20, so we have 9 over 20, and our units is just, well, the 1 meter cancels out here, and we have meters per minute, and that's equal to our dr dt. And so, if you saw that mistake, let me know in the comment section. 2 times 10 is a 20 there, Sean. So 9 over 20 meters per minute is our rate of the radius changing when the radius is 10 meters there. So our final answer here, how fast is the radius of the spill increasing when the radius is 10 meters? The rate is 9 over 20 meters per minute. We're given this problem right here. A conical paper cup is 10 centimeters tall with a radius of 10 centimeters. The cup is being filled with water so that the water level rises at a rate of 2 centimeters per second. At what rate is water being poured into the cup when the water level is 8 centimeters? Okay, so we have a conical paper cup, and the formula for that, the volume of it is pi h cubed over 3. And we get an image of this. Now, I'm going to kind of roughly write this as scale, but it's pretty wide cone for how deep it is. Right there. Okay? Now, this cone has a radius, r, and a height. Right there. Okay? Now, what do we know about this, well, cone? Okay? They said the cone is 10 centimeters tall, so the overall height of the cone is 10 centimeters, but the radius is 10 centimeters. So the height is 10 centimeters, and the radius is 10 centimeters as well. Okay. Now, we are given a rate that the water level, so the water in here, that water level is rising up at a rate of 2 centimeters per second. So the height of where the water is rising at a rate of 2 centimeters per second. And that we will call a rate, so dH dt, the height with respect to time, is 2 centimeters per second. Okay, I go SEC. All right. So what do we need to find? Well, they want to tell us what is the rate, at what rate is the water being poured into the cup when the water level is 8 centimeters. So we're trying to find our dV dt here. The rate of the rate at which the volume is changing. Okay. Now notice what's kind of conceptual here. The height, 2 centimeters per second, is the rate at which the water is increasing. All right. So the height of it. So the water that's being poured in from this hose or whatever, right, is going in, is actually increasing, right? It's going faster and faster to keep up that rate because the volume gets larger and larger. There's more volume per the height of 2 centimeters per second going on there. So more water is actually being pumped in faster and faster to keep that height at a constant rate of 2 centimeters per second. Just something to know. All right, so let's take our formula and let's derive this with respect to time. So we take our d over dt of our volume, and it's equal to the d over dt of the other side, which is pi h cubed over 3. Now, luckily for us, we can take the constant pi and 3 and kind of put it out front. All right, so we have pi over 3 here, make it a little easier, d over dt of just h to the third power. And we write this down here, d over dt of my volume. Okay? Now, the derivative of, with respect to time of the volume is just that dV dt. And look, that's something we're looking for, our answer. So we're on the right track here. Pi over 3 can just stay out front. And let's derive here height cubed with respect to time. Now, power rule, chain rule kind of going on here. Remember, h is a function of time here, or it's going to be. 3 comes out front. Power rule, h stays the same. Subtract the exponent by 1, we have h squared. Multiply that by the derivative of h with respect to time is that dH dt. Okay? So now at this point, it's a plug and play operation. Okay? We're going to plug in what we know for our variables and cancel out this 3 because that's easy to see. So we have dV dt is equal to pi times our height at the moment we're talking about here. Now they tell us this happens when the water level is at 8 centimeters. So should put that down. The height we're looking for, specifically, not the overall height of the cone. Be careful there. The height at the moment we're looking for is 8 centimeters where this happens. So somewhere like maybe around here. All right. And that height here, let's say, is 8 centimeters. Okay. Now, so the 8 centimeters, so we have 8 centimeters. We're squaring that times our rate of the height changing is 2 centimeters per second. So what does that come out to be? Well, we multiply this all out. 8 squared times 2 is a 128. We still have the pi, okay? And our units here, well, we have centimeters squared times another centimeters, that's centimeters cubed per second, which makes sense because we're talking about the rate of a volume changing and should be centimeter cubes per second. And so here, our final answer, at what rate is the water being poured into the cup when the water level is 8 centimeters, is 128 pi centimeters cubed per second. We're given this problem right here. A spherical balloon is inflated so that its radius, r, increases at a rate of 2 over r centimeters squared. How fast is the volume of the balloon increasing when the radius is 4 centimeters? Okay, first, what's the formula for the volume of a sphere, this balloon, right? Well, the volume is equal to our 4/3 pi r cubed. And if we had an image of this, I'm not the best at drawing spheres. It's like something like that. And then we say like, I don't know, the radius r. Okay, don't judge my spherical balloon right there, all right? All right. Well, what are they giving to us? Well, we are given the rate at which the radius is increasing. So the rate of the radius, dr dt, is given as a rate of 2 over r centimeters per second. Okay. What else are we given? Well, we want to find that happens when the radius is 4 centimeters, so the r we're looking for is 4 centimeters, okay? And we want to find our, well, dv dt, the rate at which the volume of the balloon is increasing. So our dv dt is what we're looking for. So what I'm going to start with my formula right here for the volume of a sphere. I'm going to derive this with respect to time, okay? So we have d over dt of the volume is equal to d over dt of 4/3 pi r cubed. Okay? Now, what's easy on the left-hand side, derivative with respect to time of the volume, is just that dv dt. Here we can pull out our constants, 4/3 pi, just out here. Don't need that there. And let's derive r cubed with respect to time. Power rule brings down the 3. R stays the same in there. Subtract the exponent by 1 is 2. Now, that's like the chain rule going on. Derive r with respect to time, and that's dr dt. And so now we have pretty much the meats here. Let's go plug in what we know, right? And simplify where we can, right? 3 cancels. That's always easy to get out of the way. So dv dt is equal to 4 times pi times our r value at this moment was 4 centimeters. So we have 4 centimeters, and we're squaring that, times, now notice here, our dr dt is 2 over r centimeters per second. So we have that put in here, 2 over r centimeters per second. But if you're confused here, it's normal, right? Well, we have a variable and our rate, what's our rate of the volume, what's going on? Well, our rate at which the radius is increasing is dependent on where the radius actually is. And so the moment we're talking about is at 4 here. So we plug that in. So we have dv dt is equal to 4 times pi times 4 centimeters squared times 2 over 4 centimeters per second. Okay? Well, let's go cancel where we can. 4 cancels right here, okay? Simplify this whole thing out, put it over here. And what do we have? Well, 4 squared times 2, okay, I'm not sure I lost my spot here. 4 squared times 2 gives me that 32. We have a pi, okay? Then our units, we have centimeters squared times centimeters, so we have centimeters cubed over seconds. Which actually makes sense because we're talking about the rate at which a volume is changing. And so the answer, they asked us, how fast is the volume of the balloon increasing when the radius is 4 centimeters, is 32 pi centimeters cubed per second. We're given this problem right here. A 7-foot tall person is walking away from a 20-foot tall lamppost at a rate of 5 feet per second. Assume the scenario can be modeled with right triangles. At what rate is the length of the person's shadow changing when the person is 16 feet from the lamppost? Oof, that's a lot of stuff. Let's go get a visual here. So we have a lamppost, all right, that's 20 feet tall. And it should be a right triangle. It's not really straight, but it's all good. Now a person is standing who's 7 feet tall, a very tall person. Okay, let's make that just a line here. Again, my straight lines aren't the best. We got 7 feet. And they're 16 feet away. And we want to find what's the length of the shadow at this moment. So we don't know what the shadow length is, okay? But what we can do is create a right triangle going on right there. I'm connecting it all here. And that light post, right, the light is up here. It's creating that shadow over that person. Put him right here. Standing. Doot doot. Very tall. Long torso. Alright. And there's creating that shadow, and this is the length we want to find. So I'm going to put some variables out here. We have right triangles going on. I'm going to put it that way. And we know things about similar right triangles. So let's give this length an x, and this is a y right here. Okay? So what do we know? How can we get a formula out of this that connects everything that we need? Because we want to find that y value. Okay? Well, right triangles, right? We know that they're similar right triangles. They're proportionate. So if I take the length x plus y, and I put it over the other leg of the right triangle, 20, that should be equal to the length of y, similar side, over the height of 7 feet for that person. And we actually have an equation right here. Okay? Now, what else are they given to us? They say the person is walking away from the lamppost at a rate of 5 feet per second. Well, if this is our variable x, then that's dx dt. The rate at which the person is moving is 5 feet per second. Okay? And we want to find what is the rate. All right, what rate is the length of the person's shadow? So not the length of the person's shadow, the rate. We want to find dy dt here. All right, so the length is that y value, with the rate of it with respect to time. We want to find that rate. So that's a tricky part here. We're not trying to find y. If we did, that's just a simple geometry problem. We want to find the rate here. Okay? Well, here's my formula, and before I dive in deriving both sides with respect to time, let's simplify this up. Multiply 7, cross multiply here, make it easy for yourself here. And we have 7x plus 7y equals 20y. From there, subtract a 7y to both sides, and 7x equals a 13y right there. And it's at this point I like to deal with this part. Okay, some people will solve and maybe get y completely by itself, but I don't feel like dealing with that fraction yet. Okay, so it's up to you. I'm going to derive both sides with respect to time. d over dt now times or of 13y. Okay? This actually becomes very simple. Derivative of the constant just comes out front, and the derivative with respect to time of x is just that dx dt. Same thing here, constant 13 can come up front, and the derivative with respect to time of y is just dy dt. Okay? And we want to get dy dt really by itself, but let's plug in what we know. Okay? We know dx dt is 5, so we have 7 times, well, 5 feet, not centimeters, feet per second, equals 13 dy dt. Divide both sides by 13 here, and what do we have? dy dt is equal to, 7 times 5 is that 35, over 13, and the rate is still that feet per second. And notice one thing here. We didn't actually have to find the length of y to solve this. So right now, which is kind of an interesting moment, we know the rate at which the shadow is increasing at this moment when he's 16 feet away from the lamppost, but we don't actually know what the shadow length is. And it's kind of a cool thing that we can find without knowing that information. Either way, the rate of the shadow is increasing, all right, or yeah, increasing when the person is 16 feet away is 35 over 13 feet per second. We're given this problem right here. An observer stands 700 feet away from a launch pad to observe a rocket launch. The rocket blasts off and maintains a velocity of 900 feet per second. Assume the scenario can be modeled as a right triangle. How fast is the observer to rocket distance changing when the rocket is 2,400 feet from the ground? So let's get an image. They say we have a right triangle going on here, we can assume. Okay? So I'm going to kind of put this out here, a little right triangle, if I can draw one nicely. Okay, so here's that rocket. All right, let me draw a little rocket here. Don't judge my drawing skills, please. All right, we have a little flare thing at the bottom here, whatever. Okay, here's my rocket, and there we go. The rocket is going up at a rate, they tell us, of 900 feet per second. So let's call this the y side. And so our rate with respect to time, dy dt, is equal to that 900 feet per second. Okay, the rate at which the rocket's going upwards. Okay? Now, the overall height, the moment where this whole thing happens, is a height of 2,400 feet. That's when the moment we're talking about, when that height is 2,400 feet. Let's call this length x, okay? And the person is 700 feet away, this little person, the observer. Okay? So we have 700 feet away, And the height of the rocket at the moment is 2,400 feet, and we'll call this length z, okay? But they're asking us how fast is the observer to rocket distance changing. So we want to find dz dt here. That's what we're looking to find. Now let's go find the length of z right there, okay? Length of z, we're doing our a squared plus b squared equals c squared, Pythagorean theorem. And so we have the length, let's go y was 2,400 feet, so we have 2,400 squared plus 700 squared is equal to z squared. Square root both sides here, and don't worry about the minus obviously because we can't have a negative distance going on here. And this actually comes out to be a nice neat number of 2,500 feet. Okay, so we got that z value calculated pretty easily using geometry or Pythagorean theorem. 2,500 feet. Got that. All right. Well, the formula here is that Pythagorean theorem. That's going to be the equation that we need. Okay, so we have our y squared plus our x squared is equal to our z squared. Okay. Now, luckily for us, we know we don't really have to worry about the x value. Okay, that's given to us at 700 feet. Same with the y value, but we'll plug it in a little bit. So I'm going to deal with that. We don't have a rate really going on with that x value. You'll see in a minute it's not really changing, but we see that here, and we have our y squared plus 700 squared equals z squared. Now I'm going to derive both sides with respect to time. Okay, so to do that, I have my d over dt, what I got going on here, and of course I did this, d over dt. Let's go rewrite that. So we have d over dt, let's do each part here, of y squared plus d over dt of 700 squared equals d over dt of z squared. What the? There we go. So many little things going on. All right. Well, here, derivative with respect to time of y squared, it's kind of like chain rule. 2 comes out, or power rule. 2 comes down. Y exponent subtracts by 1. Now the chain rule, dy dt. All right, deriving with respect to time. Plus, the derivative of a constant is just 0. Don't really need that. Now here, same thing, 2 comes down times z, just like the y, and then we have dz dt. Okay? Not too bad. Well, let's plug in, well, what we know. Or, we don't really need a 0. We can kind of erase that. The 2 cancels out right there. Don't need that either. Okay? Divide both sides by 2 and it's gone. Our y value at the moment is 2,400 feet. So we can put that in, 2,400 feet. Times the rate at which the rocket is constantly moving up is 900 feet per second. Be multiplied, 900 feet per second. And that's equal to z, which we found, 2,500 feet, times the rate dz dt, which we want to find. So now to get that by itself, we divide both sides by 2,500 feet to both sides. And what do we get? We have dz dt is equal to, well, look at the units. The feet cancel out right here, okay? And if you take 2,400 times 900 divided by 2,500, it actually comes out to be a nice, neat number of 864. Funny how that happens. And our units left is just feet per second, which makes sense because it's this linear rate changing. So when how fast is the observer to rocket distance changing when the rocket is 2,400 feet from the ground, our rate changing is 864 feet per second. I hope this video was helpful for you, and if it was, please subscribe to this YouTube channel and like this video. This helps us make more free math lessons for you and for everyone else. So as always, thanks for watching.
Minute Math, when you need help you use Minute Math.